Good morning, everyone. Good morning to everyone online as well. My name is Vuyolwethu and I'm going to be chairing the session today with our speaker, Vuyolwethu Mxo. I'm just going to give a brief bio on Vuyo. So Vuyo is a PhD student from SAIAB. She's also registered at the NMU University, Nelson Mandela University. She's part of the UNISA group. So Vuyo started at SAIAB in 2019, where she came in as an intern, and then she's gone from intern to MSc to PhD, which is the work she's going to be presenting today. So her work mostly focuses on social ecological systems, where she works closely with local communities, especially the Eastama Trust. Apart from the science parts of things, the academic side of things, Vuyo is very actively involved in a number of committees from SAIAB, including the wellness team, as well as SHAG. She's also part of Ocean Steward, which is an initiative with the World Trust and a project of White Oceans. So I'm just going to let Vuyo to come through. One thing that I'm going to ask is that everyone just keeps their phones on mute so that we don't disturb the presentation as it's going. If you have questions online, just put them in the Q&As, and then at the end of the presentation, we're going to have the Q&A session. Thank you. So
I hadn't realized that I've been to SAIAB for more than 5 years. Obviously, must think of awards for long service for students. Good morning, everyone, and thank you for joining the talk. Thanks so much for the lovely introduction. So today I'll be presenting one of my chapters for my PhD, focusing on the cultivation of Cyperus textilis for ecological engineering purposes. So this work, I was supervised by Professor Francesca from the house, and Dr. Terren Britton, and Professor Janine Adams from Nelson Mandela University. So more and more people are moving towards coastlines, and this creates coastal developments. So these reduce natural habitats, they harm biodiversity, and disrupt key ecological functions such as spawning, feeding, and habitats for wildlife. So the problem with this is that they build these hard engineering designs, such as seawalls, which are environmentally disruptive. So to try and overcome this challenge, a field of restoration ecology emerged, which is the scientific practice of restoring degraded ecosystems to a state that is close as possible to the original state. Within restoration ecology, there's ecological engineering, which is the integration of ecological principles into engineering designs. And within ecological engineering, there's nature-based ecological engineering, which is the use of natural resources and ecological processes to rehabilitate. So what is the role of plants in eco-engineering? So plants are known to be natural stabilizers. So they have these roots that prevent soil erosion. They also assist in water management because they filter and they regulate water, improving water quality. And they also assist in habitat creation for wildlife. So I'll give some examples of wetland species, plant species that have been used in ecological engineering. In seagrasses, you find species of Substera marina that are used to lessen the wave action. And in mangroves, there are species of Rhizophora, and they have large roots masses that trap sediments. And in freshwater systems, you find one example of Phragmites australis that is used in constructed wetlands, and it helps in purifying the water. So my study species is Cyperus textilis, which is locally known as imizi in the Eastern Cape. So this plant is indigenous sedge, native to the southern parts of Africa. It is distributed from Western Cape to the southern parts of KwaZulu-Natal. It is a facultative wetland species that grows competitively in freshwater environments. It's mostly found in riverbanks, streams, and dams. So this plant traditionally is being used for weaving household items such as sleeping mats and fruit baskets. But now it is being explored for ecological engineering purposes, and I'll talk more on the following slide about that. But The problem with using a natural resource at a large scale is that you risk over exploiting that natural resource. So there's an in-house project known as IMIZI project. It is a multidisciplinary project where we're working with the local community to co-create these IMIZI woven nets. So the local community that we're working with is the Keiskamma Trust in Hamburg, here in Eastern Cape. So these mats are installed in harbors and ports. Here's an example of a mat. And the goal is to increase surface complexity, providing attachment and refuge for aquatic animals. But the ultimate goal is to rehabilitate these urban coastal environments. So IMIZI project has a potential of being successful, and that would mean that there would be an increased demand of the IMIZI plant. So we need to find a sustainable way of cultivating the plant. So this is what I did for this chapter. I cultivated the plant in a greenhouse setup, and the aim was to investigate which cultivation condition yields best growth of Cyperus textilis. Our objectives were to determine which technique, that is soil or hydroponics, enhances plant growth, and also to determine the best fertilizer level for the growth of IMIZI. So how the research was designed, there were 9 hydroponics and 9 soil systems, as you can see. And in terms of fertilizer, there were 3 levels of fertilizer with 0, 50, and 100. 50 being no fertilizer, 50 being the moderate, and 100 being the extreme level of fertilizer. So there were 3 replicas for each treatment and total of 18. So IMIZI were collected from the wild and they were acclimatized to the greenhouse for 4 weeks before the experiment, and the duration of the experiment was 10 weeks. So there were weekly measurements where we measured abiotic and biotic parameters. Abiotic parameters included all the physical-chemical parameters such as pH, temperature, dissolved oxygen, redox potential, TDS, EC, and salinity. And the biotic parameters were all the growth metrics such as new shoots, which is the new plant buds, count density, which is the individual stems of the plant, height, and gum width. So in terms of abiotic parameters, when looking into the graphs, the blue is hydroponic systems and the green is soil systems. So in terms of pH and temperature, they were pretty stable throughout the weeks, and which is what we wanted to achieve because we want to keep those stable. And in terms of dissolved oxygen, there were little variations between the weeks, but there was a spike on the 9th and 10th week. And in terms of redox potential, it was lower in hydroponics compared to soil. And in TDS, EC, and salinity were higher in soil than in hydroponics. We also conducted a permanova analysis to look into the interaction between the technique and the fertilizer level. And we found a significant interaction, which suggested that the level of fertilizer that you need depends on the technique that you're using. And looking into the graphs, the red is hydroponics treatments, and the blue is soil treatments. So hydroponics had higher levels in most growth metrics, that is the new shoots, the count density, and the count width, while the soil had higher values of heights compared to hydroponics. We also found vegetative production in all treatments on the 8th to the 10th week, and we also noticed yellowing of counts in fertilized treatments, that is the ones with fertilizers 50 and 100. So this suggested over-fertilization because we're putting fertilizer every week. So what does this tell us? This tells us that in terms of growth metrics, hydroponics outdone the soil, and hydroponic system conditions are easier to manage than soil. And because what you put in is what you get, and hydroponics is better candidate for domesticating and sustainable cultivation of wildlife plant species. So this is a promising approach for plant use in coastal ecological engineering for restoration and commercial upscaling application. So So in terms of practicality, because when we were working with the local community, we were able to discover that at least you need 100 cams to make 1 mat, this 30 by 30 mat. So going back to my experiment, on average, we got 27 cams with a cam size of 0.37 centimeters and average 8 shoots per pod and a height of 29.87. So on my system, I had 1 pod. So if we were to say we are having 12 pods within 1 system, we would get 320 cams, enough to make 3 mats. And then I said earlier that there were 9 hydroponics. So if we were to multiply that with 9, we would get about 2,916 cams, which yields 29 mats. So I was just showing how flexible the hydroponic system can be, which makes it suitable for personal, local, and commercial production. And again, we're working with local communities, and they're the ones who care about this plant, using this plant. So we had to look into a simple low-cost growing system, and we found the tracking method. It requires no electricity, pumps, or soil, and this would benefit the community because they can grow Cyperus textilis and also other leafy vegetables. So this helps, again, build local skills, promotes food security, supports sustainable agriculture, and community empowerment. Just wrapping up, so for us, cultivating energy sustainably means less pressure on the wild population and creating ecological products and promoting livelihoods. And on a side note, that due to its high nutrient assimilation in the study, IMIS has a potential to be used in constructed wetlands, biofiltration, in water treatment. Just to leave you with a quote that let's build resilience with nature and not against it. And yeah, with that, I'd like to thank you for listening. Special thanks to the people that have listed here, Professor Cliff Jones for loaning us equipment during the study, William and Wesley, they also gave me stuff to work on. I'd also like to thank the INEASY team, Lisa, Esihle, Bantoni, Dina, and Matsobane. Thank you for listening.
Thank you so much, Vuyolwethu, for that very nice presentation. I'm going to open the floor for questions. So you just raise your hand and ask a question. Like, do you have questions online?
No questions yet.
Okay, I'll take.
Oh, Smith first. Thanks for that lovely presentation. I think this presentation also ties in with me especially because with my transitioning journey in terms of my traditional roots, because we use a lot of those images. So my question is, how does this project speak to our community? Because I see that you only basing it, well, your more focuses on doing the meds and all those stuff. But for us as traditional healers, we do use meds, but also we use that for our gears and all those things. So what message would I get from this presentation, so that if I were to meet my colleagues in terms of our traditional roots, so that I am able to educate them more, so that they don't take a lot of them out of the rivers or dams or streams, wherever that we get them,
Okay.
So that we all working together, so that we keep them to sustain for future.
Okay. Thanks, Ibo, for that good question. So, the message you can get from this is that this is a wild plant, so it's never been cultivated before. So at least now we see that we can actually cultivate it.
Yeah.
Secondly, is that there's another way of planting it. Instead of, if you don't have like land or space, you can use a hydroponic system to plant it. It works. Thirdly, I spoke to some of the traditional healers suggesting this idea, and they were They were very skeptical. They said, no, this plant is sacred. I can't bring the river to my home. So, yeah, but if you are open to that, then I'm suggesting this hydroponics. And I've also suggested the low cost one where you can just, I can teach you, man.
So as a follow-up to that question, but I just wanted to come to a question just now. Considering the importance of the plant itself to local communities, especially in terms of culturally and economic empowerment, do you have any plans of going back to the community that you work with and teaching them the skills that you have now?
Yeah, that was the plan, but we didn't get funding, unfortunately. But yeah, it was a plan to have like a workshop after this, where I'm presenting all these types of hydroponics, because there are different types, and some are cheap, some you can recycle stuff. But yeah, we need funding for that also.
Thanks, Will. So South Africa is a water-scarce country. How does that relate to your suggestion of using hydroponics? Is it a water-intense operation, or is it quite a low
Okay,
water use?
thanks, Matt. So hydroponics is the one that I use. I tried considering that. So it's a recirculating system. So you're using the same water over and over again. You just need to refill, because some will evaporate, but it's recirculating. So I had to consider that. The only way you would lose water is if you have leaks. Otherwise, yeah.
What sort of volumes are we talking?
It depends on the system and the amount you need.
Or
So
your scenario there that you proposed?
I had about, one system had about, I think 400 liters. It was a big sump. Yeah, I think 400 liters. So that went like for the whole study. I had to just refill some.
Do you have any more questions on the floor?
So your fertilizer concentration was too high. Do you think there's a lower value that would be optimal? Is there a value of non-zero that's better than zero?
Yeah, so I had to include 0 because we needed a reference, and for people in the local communities, probably they wouldn't have that. But if I were to, I would need to refine again the study and put more values in between the 50 and 100. But the 50 and 100 were too high for the plant.
So you need a lower value.
Yeah, I need.
Would have made them grow better.
And an interesting fact that I got from my other chapter with the local communities, that they don't really use fertilizers for planting their own, and they use manure. So I would definitely go lower than 50.
We have a question from.
Thanks, Vuyo. Yeah, you gave a really nice background, and you took everyone with you. So I also have a better understanding of the the project. If you had to go hydroponics, the hydroponics route, I'm just looking at the potential cost implications there versus the economic benefit.
Okay.
If you looked into that to say, okay, because you may need, massive investment, including the pumps, the fertilizer that you're going to use, and all that, and even the the number of people that are going to work with you to make the maths and all that.
Yeah.
How does it translate in terms of the economic benefits that would come out of the investment of that nature? Have you looked into that?
I have looked into that, but it's a different chapter. But hydroponics really depends on the scale you want it. So let's say SAIAB goes for commercializing the nets. Then that would mean that we need like a proper hydroponic system. And that is a bit expensive, but it's very efficient, and there's a short turnover of the growth of the plant. So I have looked into that, but yeah, it depends really on the size of the system that you want and how many systems you need. Yeah,
but
if you want a large scale production, then it's going to be more expensive than Yeah.
Maybe because I know you're wrapping up your pieces, right? So you've already looked at the ecological engineering, where you've introduced the nets into the transformed system, marine system. And how is it looking there in terms of facilitating?
Okay, so that part of the research is Nobush's.
Okay.
Nobush's section. So she's looking into the recruitment and how the nets are working. But are you saying, you know, the nets are working?
Thank you.
Yeah.
Thank you.
Do you have more questions online, Lucky? Questions on the floor? Nothing. Thank you so much. Thank you, everyone.
Thanks so much.